This case to be lava tubes. Parts are even still volcanically active. Small hydrothermal vents release smoke into the caves that slowly settles like rain. If you can model how the smoke flows through the caves, you might be able to avoid it and be that much safer. The submarine generates a height map of the floor of the nearby caves for you, your puzzle input. Smoke flows to the lowest point of all the area it is in. For example, consider the following height map. So for each point in here, we are going to find the points where it is the slowest of all of its neighbors. So we need to find all the points here that are the slowest of all of its neighbors and the thing like that. So, you know, if you can think it's kind of like mountains things, we want to find like the depressions kind of thing. Your first goal is to find the low points, the locations that are lower than any of its adjacent locations. In the example above, there are 4 low points. We don't consider the diagonals, okay? So just up, down, left and right. In the above example, there are 4 low points all highlighted. So this one, and this one. The risk level of a low point is 1 plus its height. In the example above, the risk levels of the low points are 2, 1, 6, and 6, and therefore we need to 7 to 15. So let's get started. Let's get the input. Get this. All right, so here's our input, and we are going to split this into new lines as usual, and then we need to trim at the end. So those are our rows, right? We also want to map over those rows. Actually, I'm not going to map over those rows. So the first question is how we are going to represent this, okay? How we are going to represent this in terms of the structure. And I'm thinking about representing it as a map that says like 0, 0 is going to take to this number 2, right? And then 0, 1 is going to take to the number 1, 0, 2 is going to take to 9. So that's what I want to do, okay? So in order to do this, we are going to build the grid, okay? So I'm going to use a for comprehension. So this is already going to be slightly different so what we do in the other days, okay? So we are going to do this. This is going to give the lines. And now we need to get the numbers. How are we going to get the numbers, right? So we need to get the columns. And actually, we need to know the index, right? So I'm going to use with index here, okay? Starting from 0. How many arguments with index expects? Do we have a version? Yes, it's optional. So let's do with index here. So this is the line, and this is the, let's say the row, and then this is going to be the number, and this is the column. And the numbers, the way we're going to get the numbers is that I'm going with index as well. And I'm just going to do a string to char list, okay? So why string to char? I'm going to explain why very, very soon. Hold on just a second. Off the line, and that's going to give us that. We know that our keys are row and cols, and our numbers are going to be this, right? So you can see that we are getting everything that we want, right? So this is pretty good, except that the numbers here are off because we converted to char list. So 0 in char list, it's actually 48, I think. So we are going to do the offset of 0, and now we get the representation that we want. And we want to store, and now it's returning everything as a list, and we want to store it in a map. So I'm going to say I want to put that into a map. And now we get a map, we have our grid, maps inside maps. This is a good trick, right? A lot of the times you don't need to put maps inside maps if you can just like have the key be the nested structure that you want to look up for. And many times that can actually be more efficient, maybe not, maybe yes. So we have the grid, and now we have to find the lowest points. So the way that I'm thinking about finding the lowest points is not going to be the most efficient version. So the way that I'm thinking about finding the lowest points is just go literally point by point and see, hey, am I the smallest of my neighbors? Okay, how we are going to do this? We could use a reduce. This is equivalent to reduce, but now we're going to use the reduce now. We are going to reduce over the grid. Wait, no, do we want to reduce over? No, we want to filter. We have the grid. We want to find all the positions in the grid where I am the smallest compared to my neighbors. We are going to receive the row and the column. It's a tuple with the row and the column, and this is the value. Okay, we don't care about the, no, we care about the value. So what we are going to do, we are going to go through the grid and get row plus 1, col plus, so if you are here, we want to do row plus 1. No, we don't do that. This is a movement in the diagonal. Okay, And before we do this, there's something I want to check. Does this work? It works. All right. So we want to find the minimum, right? And the minimum between 2 and 6, right? It's going to work. It's going to be 2. But the thing is that when we are in the corners, the values are going to be nil. And the question is, what is the minimum between 2 and nil? If it's 2, then we can rely on minimum. If it's not, we need to take nil into account. So it's 2, so we are good. Nil is smaller than 2. To clarify, for those who are not familiar with Elixir, in Elixir you can actually compare everything. You can compare a number with an atom. You can compare everything. So we have a total ordering of the terms. The order doesn't matter the huge majority of the time, like how you compare between terms. And the reason it is like that, it comes from Erlang. It's for a convenience. If you need to do sorting algorithms that compare everything, it can do that. Okay? So let's go back here. So what we need to do is that we need to say, look, can I have equals? I'm assuming that we can't have equals. I assume that, oh, we can have equals. So what happens in the equal case? Am I a minimum? So let's read the description of the problem. It needs to be lower. So we cannot have equal. Let's say this is up. It's wrong here. So this is up. This is down. This is left. And this is right. And then what we want to get is the one where the value needs to be less than up, the value needs to be less than down, and the value needs to be less than left, and the value needs to be less than right. I think this is it. So it gave us all the 4 points that we're interested on. So this is good. We filtered them, but we still have the positions and the values. We know we want to get the value plus 1, and we want to sum them. Okay? This is going to be 15. So we solved part 1. Wouldn't be up be minus 1? You are correct. It doesn't matter, but you are 100% correct. The score is height plus 1. So that's what we get here, height plus 1. Minus 1 plus 1 left. Yes, I think we are all good now. Thank you. Thank you very much. Yeah, the thing that we're doing different is that we are already starting with a 4. We used 4 the previous days, but usually parsing the input was just like a bunch of pipelines and would get a list. I think it's the first time well, maybe the board as well, but yeah, but that's the kind of different thing that we are doing so far. Let's put my actual input, the input that they are going to give to me. So we are going to do a setup. We are going to install Kino, and Kino is a package that allows us to make Livebook interactive. So we are going to install that. We are going to have an input here, which is Kino input. This is going to be a text area. Please paste your input. And now we can take this, we can put it here. This is going to be too ugly to put everything to a single line. So let's do this. Input, don't need to save. Then we're going to do Kino, input read. So we read the value of this text area that we just inserted here. And now we are going to string split over that, which is this code here. And now we're going to put the lines here. So this should still give the same answer. It's very likely that we're going to use the grid in part 2. So I'm going to move this to this shared code as well. So now we have the grid, and the grid is coming to this part, and it's 15. So now I can get the puzzle input. So one of the cool things is that we can say that this input reevaluates automatically. And now when we paste the new input in here, we should get the new answer automatically because it just reevaluated, and it took only 200 milliseconds, so that's pretty good also. Let's see if that's good. Let's see if that's the answer. All right, part 1 is done. Let's do part 2. Next, you need to find the largest basins so you know what areas are most important to avoid. A basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin, although some bases are very small. Locations of height 9 do not count as being any basin, and all other locations will always be part of exactly one basin. The size of a basin is the number of locations within the basin, including the low point. The example above has 4 basins: top left basin size 3, top right basin size 9, top middle basin size 14, and top right basin size 9. Find the three largest basins and multiply their size together. In the example above is 9 multiplied per 14 multiplied per 9. 134. I think we can do it. I'm going to go like the not smart way at the beginning, and maybe it's going to be bad. Maybe I'm going to have to optimize it. So I'm going to copy the original input so we start working on something smaller. And these we want to reuse, so I'm going to bring it back here. Those are the low points, right? Low points. Let's store it here. We are computing them from the grid. Let me format this, and then here we're going to get the low points. We are going to map them. This is part 1, and this is part 2. All right. Oh, this is part 1. It didn't change, so now we're going to start part 2. All right, so let's go back here. We have the low points, all right, which is the lowest points of the thing, and those are going to be our initial points. My idea is to, from each initial point, go to my neighbor and say, hey, ask if it's the smallest, right? And if it is the smallest, right, we are going to add to us, and so on, so on, and so on, recursively. Wait, do we want to know if it's the smallest? Smallest except the place I came from, right? So it's like smallest but me, or, well, if I have 2, then that's the smallest. That considers me. I'm wondering what happens if I have 2 equal numbers, if they're going to propagate, or it's not possible to happen in the input. It seems like it's not possible. The only places that are equal numbers are the 9s. It's more like you stop at 9. Oh. That's easier then, isn't it? It's always stop at 9? Okay, thanks everybody for clarifying that. So I'm going to start with the recursion. I'm not sure if it's going to be necessary, but from an initial look at the problem, I feel like we're going to need a recursion. And I feel like we are going to need maybe a map to store the parts that we visited for each number. 9 or edge. Yeah, 9 or nil then, in our case. Okay. Wait, I have the low points, right? So for each low point, I need to compute, what do they call it? They call the basing, right? We need to compute the base. So we're going to receive the row and the column of the low point. We are going to receive, we don't care about the value then, right? The value is not relevant. I mean, the value where we start, we just want to go until we find a 9. We are going to, the basing, I'm almost sure we're going to need an accumulator. We're going to need a count. Okay, so we're going to say an accumulator where we're going to store, hey, have we been on this part of the thing? And if we have been on this part of the thing, then we don't go any forward. Otherwise, we do. Okay. So actually, let's do this basing. It's the basing size rather, right? That we are doing here. But we need to know if 2 things are part of the same basing, and that's going to be a complication that we'll have later. So I'm going to use the scene for that. Okay. All right. So, all right, let's get started. We want to get the basing, and then from the basing, we're going to get the size. So I'm going to use a map set, okay, to store. So map set is a set, right, to store the things we have seen to make sure that we don't come back. So, and the map set is going to start with the initial position, okay? And we are also going to have so basing, and then we need to no. We're going to start with an empty map set. We are going to start with a count of 0, and we need the grid. We need the grid too, okay? So here's the recursion. What we're going to do is the following. We are going to say, look, for this basing, right, that is this row and column, and we have a grid, and we have the set, and we have the count. We are going to say, look, is this row column in the set? In other words, have we seen this point? Have you already gone through it? If we have gone through it, then we just return, what do we want to compute? We want to compute both the set and the count, right? No, the count we can get from the map set. So we don't need the count. So we just need the set. So we're going to return the set unchanged. If we haven't seen the point, we are going to store it in the set. Is it add? But, okay. Kind of weird that it's but for the set, but it makes sense with the whole vocabulary that we have. So we are putting in the set. It's mathematically weird, but it's elixir logical, if that makes any sense. So we're going to put it in the set, and we're going to say maybe basing. And maybe basing is going to receive a coordinate. It's going to receive a grid, and it's going to receive the set. And the idea of maybe basing is, I'm going to pass the set as first argument. I'm going to change things a little bit. Hold on just a second. We don't need, this is the coordinate, right? Let's call this point. Hold on, I'm just moving some things around very slightly. So this is the point, this is the set, the point, and the grid. Okay, so if the point is in the set, we return the set. We don't need to go any further because we already visited that place. If it is not, we put it in the set. And now we are going to say, we are going to do a pipeline, which is going to be this. We're going to put the point in the set, and we're going to call maybe basing, okay, with a point, all right, and the grid. And we're going to say, look, we're going to look in the grid, all right, for the point and say, is this point 9 or nil? If it's 9 or nil, we just return the set. We don't want to continue, right? And if it's not 9 or nil, then we are going to call basing, passing the point and passing the grid. So we are going to go back here. We are going to see if the point is there, and if the point's not there, actually this could all be here in this same function. So we are going to see the point in the grid. If it's this, we return the set. Well, if the point is 1 or nil, or the point is in the set, we return the set. Otherwise, we are going to have this beautiful pipeline, which is going to be, could be like, hey, I need the row and the column here. And then we're going to say, look, go to the basing, row +1, and then the column and the grid, right? And then we are going to do, let me copy this 4 times. So we are going to go up, we are going to go down, we are going to go left, and we are going to go right. Okay, I don't think we need this. All right, so we have all the low points. Let's compute the basing for them. I'm going to stop really soon and do a recap of this because this may not be the most straightforward thing ever. And I'm getting 4 empty map sets, which means that none of this is working, which means there's no point of me trying to explain it. Or point in set. Oh yes, I know why, right? Because the point here, let's do this so we don't, wait, why? Ah, yes, okay. So this is the point, this is the value, and we don't care about the value. So I'm from Brazil, but I live in Poland right now. And I mean right now, and most likely permanently, right? So, okay, we got 4 basins, all right? And one has 3. Let's do this. Let's see if this is correct, and I'm going to explain everything that is happening here. And, okay, no, let's get the map set size. 14,939. Is this correct? 14,939. Okay, it's all good. All right, so we did part 2. All right, I'm going to go ahead and explain what I'm doing here, okay? For each low point, right? So for each low point that we found on part 1, 2, 0, and 2 other things in here, we, as people said, we need to start expanding until we find a 9, right? Or until we find a nil, okay? And so what do? We get a map set, and the key in the map set is to store points that we have already traversed. This simplifies the algorithm a lot because we can kind of just say, go like, when I move to this point, I don't need to say, hey, don't go back here. We don't need to store this logic because we put that we visited this point. So when we go to this point and say, hey, visit here, we say, oh, we already visited, so we come back. It's not the most efficient approach, right? There's a lot, every time we go to a point, we visit the neighbors, even though we know we were in the neighbor, but it may be good enough. If it's not good enough, we optimize it, right? So we say, look, am I a 9 or am I outside of the grid? If I am a 9 or outside of the grid, I'm not going to do anything. If I have already been seen, I'm not going to do anything, right? But if it's none of those cases, I am a new point, I should be part of the basin, so I'm going to store myself in the basin, and I'm going to do the same thing for up, down, left, and right. That's it. That's the basic recursion of the algorithm. All right. So there are a couple things, and this is going to return to us map sets. So sets with all the points in the basin. And what we want to do is that we want to hold on, let me think about this. These may be very expensive, okay? No. We want to get the unique ones. Let me see if we can optimize this. No, we need to sort everything. And then do we have stream unique? No. We want to sort everything and okay. I'm going to do the expensive version, right? Because the things that 2 points may be part of the same basin, I think. It may happen in the final input. So we need to call unique to handle those points. And then we are going to do a sort by on the map set size. And after we do this, we want to do a desk thing, right? So, and then we're going to take 3. So, well, actually, we just want to do, we can do the map size here, and then we can do a sort desk, and then we take 3 and we do the products between them, right? 1, 1, 3, 4, okay? Let's try it in the final input, and then if a point cannot belong to more than one basin, then this is unnecessary. Does it say so? Oh, you are correct. All other locations will be part of exactly one basin, so it's all good. We don't need this. So what we need from this is something like this. This is going to return the map set. So thanks once again for having my back. We don't need to, we can simplify this a little bit. And all right, cool, perfect. So I think we're good. So I'm going to get my puzzle input again. We are going to put it there and we're going to see if it works. So it was quite fast. Good. I was a little bit worried. 40 milliseconds. This is perfect. Let's see if it's correct as well. Yes, it worked. All right. Since when is there enum product? Oh, enum product is very recent. I think 1.12. We added both tuple. We had a tuple product as well because when we started working in an X, we realized that using tuples to specify points or coordinates or grids is very common. So we added tuple size, tuple product. We added tuple sum and tuple product. We already had the num sum, but we added the num product in 1.12.